Welcome to the Deep Dive. We take complex topics, pull out the essential insights from various sources, and, well, deliver them straight to you. Today we're talking about something fundamental, almost invisible, that powers basically everything digital. APIs. Picture this, a small startup doing okay on a simple system. Then boom, overnight success. They quickly switch to microservices to scale up. Sounds great, right? The dream. Well, not quite. Their public APIs started crumbling under heavy traffic. They were sending huge chunks of data when users just needed the latest update and adding new features. It became this total mess, almost sinking their growth, this kind of chaos, this something you might be facing, or maybe you're just curious about how to avoid it.
Exactly. And that's really our mission today. That startup, they learned the hard way, outages, unhappy users, the whole deal. But we're here to give you a shortcut. We've distilled their experience, along with best practices, into 7 key points for API design. The idea is you walk away not just knowing stuff, but with some maybe surprising facts and practical insights, things you can use to build better systems or just understand the tech behind the apps you use every day.
Okay, let's dive in. The absolute foundation first, REST. We hear this term everywhere. But beyond the basics, what's maybe a subtle point about REST that often trips up newer developers, especially when it comes to scale?
Yeah, good question to start. REST, representational state transfer. It's not like Terfit, a strict standard. It's more an architectural style. Guiding principles, really, the core idea. Organize data into resources, give them unique URLs, interact using standard stateless methods, usually HTTP. Think of it like a library. One entrance, books on shelves by subject, each with a unique call number. You use get to borrow a book, posty to add a new one, putty to update it, delete to remove it, simple verbs for clear actions.
Right, so that structure makes interactions really clean, predictable. But you mentioned a subtlety, a common mistake.
Absolutely. The statelessness is key. Every request has all the info needed. The server forgets about you between requests. Great for scaling, right? Any server can handle any request. But the mistake, trying to force every single action into those standard verbs, like, say, publish a draft. Is that a PUT? A post. Some try to stretch PUT to mean update and publish, or post for create and publish. That gets messy. It starts looking like RPC over HTTP, basically tunneling commands, which makes the API less clear, harder for others to use correctly. So the pragmatic thing for you, sometimes creating a new specific resource or endpoint that clearly says publish draft, even if it feels less pure REST, is actually better, more maintainable, more understandable than bending the rules.
Ah, okay, that makes sense. Balancing purity with practicality. So things go wrong. It's inevitable in tech. Beyond just sending back an error message, what's the absolute first critical thing a good API does to make failure understandable?
Consistency and clarity in error handling. That's number one. You need clear messages and, importantly, the right HTTP status codes. So the client immediately knows what went wrong and hopefully why. A generic 500 internal server error. Useless. It's like being at the airport, your flight's canceled, and the board just flashes error. No flight number, no reason, no options. Hopeless. A good API error is like that departure board telling you, Flight BA123, canceled due to weather, please see agent at gate 5 for rebooking. Actionable information.
That airport analogy really brings it home. So the status code is the big picture.
Exactly. 4XX codes mean the client did something wrong. 400 bad requests, 404 not found, that kind of thing. 5XX codes mean something blew up on the server side. Our fault, basically. Then, the response body. That should have structured details, like an error code specific to your system, a message for humans, maybe even a link to docs. But, and this is critical be careful what you put in that message. Clarity is key, yes. But don't leak internal details. No stack traces, no database schema hints and public errors. That's a security risk. It's a fine line between helpful and handing over the keys. Many developers, rushing, get this wrong.
Right. Helpfulness versus security. A tricky balance. Okay, so we know how to handle failures. But what about improvements? You want to add features, maybe change things, but without breaking all the apps already using your API. How do you manage that evolution?
That's where API versioning is just essential. You have to label different versions of your API. It stops new changes from wrecking things for existing users who rely on the older setup. Think of publishing a new book edition. The old copies are still out there, still work fine, but the new one has updates, maybe fixes. Readers can choose when or if they upgrade.
Makes sense. Like software versions, really. How do people usually do this? What's the common practice?
By far the most common and usually recommended way is putting the version right in the URL path. So https.app.com/v1 items, then later https.app.com/ve2 items. It's super clear which version you're hitting. You sometimes see it done with HTTP headers too, using content negotiation like accept.applicationvnd.api.v1 plus JSON. Less common, maybe a bit more complex for clients.
Okay, URL path seems straightforward. But I can see how this could add clutter, maybe overhead. What's the real cost or trap people fall into?
You're spot on. It does add overhead. You have to maintain multiple versions potentially. Code branches, routing logic. It adds up. The big mistake, versioning every little change. I've seen teams get totally bogged down creating v1.1, v1.2, v1.2.1 for tiny, non-breaking tweaks. They think they're being safe, but they create this maintenance nightmare. Versioning sprawl, I call it. So the advice for you is crucial. Only introduce a new version v2, v3 for breaking changes. Changes that will break existing clients. Small additions, bug fixes. Usually you can add those to the current version without needing a whole new version number. Use it judiciously. It's vital, but needs planning.
Use it when you have to, not just because you changed something. Got it. Now back to our startup's other big problem. Those traffic spikes, knocking their APIs offline. How do we protect APIs from getting overwhelmed?
That brings us to rate limiting. It's basically about controlling how many requests a single client can make in a given time period. It's not just about stopping attacks, though it helps there too. It's about fair usage for everyone and stopping your servers from melting down. Imagine a free sample stand at a store. You tell people, okay, 1 sample per person per hour. Sets expectations, prevents chaos.
Okay, like setting ground rules. How does the API actually enforce that limit?
Well, technically, every request goes through this rate limiter check first. It keeps account for each client. If you go over your limit, say 100 requests per minute, any more requests in that minute get rejected, usually with a 429, too many requests status code. But good APIs don't just block you silently. They include headers in the response, like X rate limit showing your total quota, X rate limit remaining showing how many you have left, and X rate limit reset telling you when the counter resets to 0. That transparency helps clients behave well. Now, for you, 2 key things. Set reasonable limits. Don't choke legitimate users. And critically, limit by API key if possible, not just IP address. Why? Because lots of users might share one IP, like in an office or cafe. One noisy user on a shared IP could block everyone else. Using an API key ties the limit to a specific authenticated user or application. Much fairer, much more accurate. I remember early on we launched an API, no real rate limits, disaster. One script went wild, tried pulling everything, almost took us down, lesson learned fast.
Oof, yeah. Real-world pain teaches quick lessons. Okay, the other data problem they had, sending massive data sets. If you've got millions of records, how do you send that to a client efficiently? You can't just dump it all at once, right?
Never.
Especially if it changes often.
Exactly. That's where pagination is absolutely key. You break the huge data set into smaller, manageable pages or chunks. Instead of trying to send a million items, you send maybe 20 or 100 at a time. Lower latency, less bandwidth, much better user experience. It's like reading that huge 1,000-page book 1 page at a time, not trying to absorb it all instantly.
Makes total sense.
Yeah.
What are the main ways to implement this page turning?
2 main styles dominate. First, the most common one, offset pagination. Here, the client asks for a specific page number and a limit per page, like not page 3 and limit 20. Give me page 3, 20 items per page. The server calculates an offset like skip the first 40 records and uses database commands like limit 20, offset 40. Simple to understand, simple to implement. And you can jump straight to, say, page 50 if you want.
Okay, offset sounds easy. But you mentioned data changing often. If new items are added while I'm paging through, could page 3 suddenly show different stuff, like I miss things or see duplicates?
You've nailed its biggest weakness. For you, dealing with large datasets that change frequently, offset can be a real pain. First, performance. Asking for page 10,000 means the database might have to count through 9,999 pages worth of skipped records. Slow. And second, consistency. Just like you said, if items are added or deleted while you're fetching pages, page 3 might suddenly be missing items from page 2 or show duplicates. It gets confusing fast. So the alternative is cursor pagination. This is generally better for large dynamic data sets. Instead of page numbers, it uses a cursor. This is usually a unique, opaque pointer to the last item you saw on the previous page, maybe its ID or timestamp. Your next request says, give me 20 items after this cursor, like .cursor abc and limit 20. It's much faster for databases, especially with indexes, because it doesn't need to skip records. It just starts reading from a known point. And critically, it's consistent. Even if data changes, you always pick up exactly where you left off. No missed items, no duplicates. The downsides: it's a bit more complex to implement, and you can't just jump to page 50. You have to page sequentially. So for you, the choice depends. Need random page access, and data is small static. Offset might be fine. Need performance and consistency with huge changing data. Cursor is almost always the better bet.
That's a really clear distinction. Okay, let's shift to something critical. Actions that absolutely must not happen twice, like payments. How do we build APIs that guarantee an operation executes once and only once, even if the network is shaky and the user retries?
That's idempotency, a fundamental concept for reliable systems, especially distributed ones. An idempotent operation means doing it multiple times has the exact same result as doing it just once. No harmful side effects from retries. The classic example is avoiding double charges, sure, but it's broader. It enables safe retries for any state-changing operation when networks fail or clients time out. Without it, those little network blips, they can silently corrupt data if retries aren't handled carefully. It's a subtle but massive source of bugs. I heard somewhere that implementing proper idempotency cut down payment-related support issues by over 40% for one company. It solves real pain.
Wow, 40%. That really underscores its value. So how does an API actually make an operation idempotent? What's the mechanism?
The most common way involves an idempotency key. The client generates a unique identifier, like a UID, for each specific attempt at an operation. They send this key in an HTTP header with the request, say, idempotency key, some unique value. When the server gets the request, it first checks, have I seen this key before? Usually it looks it up in a fast cache, like Redis. If the key is new, the server processes the request, like charging the card, stores the result, success, failure, response data, associated with that key in the cache, and sends the response back. If the same key arrives again later, maybe due to a network retry, the server sees the key in the cache, skips the processing, and just returns the saved response from the first time. Once and only once. There are other ways too, like using unique constraints in your database or features and message queues for async tasks.
Okay, client sends a key, server checks it, processes once, caches the result. Sounds robust, but also complex. Added state, caching. When is it truly essential versus maybe overkill?
Good point. It definitely adds complexity and infrastructure cost. So for you, it's about being strategic. It's absolutely non-negotiable for any API call that changes state and where retries could cause harm. Payments are the obvious one. Creating user counts, transferring funds, placing orders, anything sensitive. Get requests. They're inherently idempotent. Reading data twice doesn't change anything. No key needed there. But for critical post, PUT, patch, delete operations, especially involving money or core data, the overhead is almost always worth it. It prevents data corruption, avoids angry customers, saves hours of manual reconciliation. It builds trust. It's often the hidden bedrock of a reliable service.
Makes sense. Prioritize it for the actions where duplication would be a disaster. Okay, last major topic. Empowering the users. How do we give you, the API consumer, control over exactly what data you get back and in what order?
Right, this is about filtering and sorting. Two sides of the same coin, really. Letting the client shape the response. API filtering lets the client add parameters to narrow down results, like status active region EMEA. The server then applies these conditions and only sends back matching items. Huge performance when less data over the wire, less client-side work, way better than fetching everything and filtering locally.
Okay, filtering narrows it down.
And sorting.
API sorting lets the client specify how the returned results should be ordered, usually with parameters like .sort created or order desk. The server adds an order by Y clause to its query. This makes the data much more usable, chronological, alphabetical, by price, whatever makes sense for the user.
Both sound incredibly useful for the client. But from the API provider side, what are the potential traps or performance hits to watch out for when offering these? Another good question. For filtering, the main complexity is on the server side. You need robust logic to handle all the filter combinations safely and efficiently. And crucially, you need good database indexes to support those filters. Offering filters on unindexed columns, that can kill performance on large tables. A common trap is offering too many filters without thinking about the database impact. Similarly for sorting, it's great for usability, but sorting huge data sets on columns without proper indexes, that can be incredibly slow. The database might have to do a lot of heavy lifting. So the takeaway for you: implement filtering and sorting thoughtfully. Focus on the fields users genuinely need to filter and sort by. And always ensure you have the right database indexes in place to back them up. Empower users, yes, but do it smartly.
Right, index. So wrapping up, we've covered a ton today. REST principles, error handling, versioning, rate limiting, pagination, idempotency, filtering, sorting. It really paints a picture. Those startup struggles we started with, they weren't just random fires. They were symptoms of not having these best practices nailed down, practices that really make the modern internet work reliably.
They absolutely do. And the common thread for you is consistency, predictability, and designing for scale from the outset. Good APIs aren't an accident. And beyond these 7 points, don't forget the basics. Clear, thorough documentation is essential. Useful error messages we talked about. And robust monitoring to know when things do go wrong. These support everything else.
Definitely. So here's a final thought for you to chew on. Think about all the apps you use daily. How many rely on these hidden API rules just to function? What parts of API design do you think get overlooked most often when people are building new things? And maybe, how can understanding these practices help you spot better solutions or even build them yourself?
It's a fascinating space, always evolving. The journey of understanding system design, both the theory and the messy reality, never really ends. Keep digging deeper.